Hello. So thank you again, Professor Baldwin, for your second lecture. And
okay, thank you. Okay. Yeah, let me do this in this order. So, just a quick notion of what we did last time. We worried about the doxologist challenge. How do you identify an isomorphism type? And saw that in order to really make sense of this question, one had to do something on the line of at least we had to do something on the line of Carnap's frameworks. And we laid out frameworks that might, roughly speaking, be called naive, informal, formal, and philosophy. And these frameworks specify the kinds of language you can use to address things. And in tune with Carnap, if you don't know the framework, you really don't. The question isn't well posed. And then we talked about the role of area in Book 2 of Euclid, and this algebraic interpretation that Vey and van der Waerden were pushing 40 years ago, and how it just misses entirely the point of what Euclid was trying to do. But they're the same notions in some sense, right? There's some meaning here. They're certainly using the same words, but whether you're talking about shifting around polygons or measuring them and doing algebra are two very different things. And then we passed on. I'll make a quick detour to this picture. Oh, I got the right one. Yeah, this. That similar triangles have proportional sides. And conversely, I guess, is 6.2. I think this is really the sort of base of Birkhoff's axiom 4, which is a variation on this with numbers in it and so on. But that's not my goal for today. But just to remind you of that picture, it's going to come back in a little bit. But oh, wait a minute. So we were, where did it say lecture 2? Yeah, okay. So I got out of order. Okay, all right. So the point here is that Euclid, before doing this, the first 3 books are geometric. First 2 I've talked about. The third is circles, and well, maybe the circles are 3 and 4. I'm not sure. And then 5 is this notion of proportion. And so here's again one of the things that it's worth putting up and then looking at, but it's only. Oh, did you? Yes, I guess I have on the next slide questions. Yes. So take a little look at this and think about issues like, well, who's using proportional reasoning today? What does magnitude mean? Give some examples. Sorry. Are there other ways to describe proportion? And are numbers magnitudes? So think a little bit in your groups and see what we can. Oh yeah, I think this is what should be there to be thought about. Well, it's good to think, but I don't hear many people talking to one another, right? And part of this is to contrast views. Yes. I think you were saying something that I don't understand Portuguese. I just saw your hands, and I think you were saying something I wanted to hear. So can you tell us about what you were? Yes, good. That's exactly what.
Definition of magnitude.
Whoop, what happened? What did I do? Oh, right. No, it's supposed to be. I thought did we plug it in? Wait, I thought we added a power, but oh, this is only the connection. We needed. They gave us some power last time. I misunderstood. Yeah, it'll work, but we'll help. Yeah, okay, we will. Yeah, if it stops, then we. All right. So yes, so go ahead with what you.
On definition 1.
Yeah.
Is a definition. It's not a definition of magnitude, but
No.
when a magnitude measure another one.
Okay, and how is it a definition? That's what I was just looking at this and realized I hadn't thought about it. What does it mean to say that the less measures the greater? I mean, I have two guesses, and I don't know which one's right. What would you think?
I think that this is related to definition 2, that says that all magnitudes are comparable.
Yes, or not. Well, at least some are comparable. It is a multiple when it is measured, so it may not be measured.
Okay.
Right. I mean, I'm sure that's central because the irrationals are exactly the things that can't be measured. That's the. Yeah. Yeah.
Definition 1, it seems a little bit like the Archimedean principle, like you have a way to measure.
Yes, I mean, and that's yeah. I haven't really tried to analyze these in detail, but certainly, definition 5 is pretty much Archimedes, I think, but I don't know that Euclid realizes that. It's certainly not made explicitly an axiom, I guess, until Archimedes, which is a generation later. Yeah. Yeah. Yes. Yeah. Yes. Yeah. Right. Exactly. And so it's again. This is how this notion is getting developed, and in this case, I think that there's maybe 2 generations before from a kind of an inkling of it to Archimedes being pretty precise. So I ask another couple of questions. How is proportion used today? Does it show up in the schools? In primary, or not primary, I don't think, but grade school or high school? Where?
Fractions and like in and that's a rule, aquela regra de três, né? Similarities.
There's one of the sciences where it's
theorem.
particularly prominent, at least in U.S. education, chemistry. Yes, right. I mean, the whole things of and this that it's less prominent is a recent feature. When Hardy proved the Hardy-Weinberg theorem in 1908, he phrased it entirely in the language that would have been understood by Euclid. The real turning over to do so that multiplying fractions is the way you think of proportion. Is a 20th century phenomenon, as far as I know. One of the great mathematicians of the early 20th century phrases the argument in terms of proportion, and in particular, he's using proportions of three things. So it's so this just off. Yeah, we're going to have a power source here. I have one, but. Spent a good deal of time this morning making sure I had it, and now here it is. No, that's not it. Yeah, here it is. That's what we need. Oh, it didn't work, huh? Well, yeah, so this notion of proportional, and I think the Chinese have in their 7th or 8th grade time course have a good grasp of proportion that is more than is done in the American schools today. So what else did I ask? Well, what are other ways to describe proportion? Yeah, some sort of linear function certainly is another one. And
in terms of functions,
and ratio, of course, is our notion of rational number, but was very definitely not a number for Euclid. But you could compare ratios. And so are numbers magnitudes. No, I think not. And that is, numbers really are discrete and magnitudes are continuous. Now that, I don't know if that's, I don't think there's anything here that tells us it's continuous, but that but being able to do the division is making things, that's the sense in which it's continuous. We aren't talking about limits yet, although limits certainly are in eudoxus. Okay. All right, so this is one that we've talked a bit about this, but I wanted to emphasize the focus that this is so this, I think this is what Louisa said just a minute ago. This is basically Archimedes, right? That if they are, there's some multiple, the other exceeds and back and forth. Right? So that's a definition of commensurability. Now, the 6.1 is the theorem that triangles and parallelograms which are under the same height are to each other as their bases. So we knew that two triangles with the same base have equal area, and that we proved in 1.35. And the crucial point of that, remember, well, I think I've got it on the next slide. But here, it's saying that you only need to know the ratio of the bases. And this is a glitch that we will talk a bit more later. So in fact, this is exactly the point. The proof of 6 point of this theorem uses both the theory of area and something about proportion, and kind of sneaks in Archimedes basically in the form of definition 5, but later commentators realized that this was not a definition, it was an axiom. And I don't know if I've said, Ian Mueller has a book about the logic of Euclid's elements, which is really a great source for this stuff. And now, how are you going to fix this? And the basic problem is you want to know that if you have two numbers, they have a ratio that you can divide. And Descartes formulates a way to describe this in terms of multiplication of segments. And I'm going to go through that, sketch a bit of that now. And Hilbert is giving a much more formal version of that in 1902, or 1902 in the United States, 1899 in Europe. But making clear again this business about what numbers are. Even the notion of what a natural number is very different for Euclid, because 1 isn't 1. It's not a number. We're counting units. Numbers are things that count the units, but the unit isn't a number. And of course, this helps. If you want to count apples, you don't say, you have to say 1 apple in our language, but it's the unit is an apple, and if it's bushels, then it's bushels of apples. It's not. So the unit is is an object of a different type than the things that the countings are the same no matter which, but where you are, but the units aren't. So a number is a multitude of units, and so I think all mathematics, at least any time in the 20th century, one is a number, and for logicians and set theorists, 0 is. So again, there's these variances, but the other question is things like, what does subtraction mean? And do you have division at all? Now, these are two separate issues. When you have this segment multiplication, that's multiplication of positive numbers, unless you're a little careful and say, instead of starting here and just going off to the right, I will go to the left, and then I have a little more complicated definition. I think I give the definition for the positive ones on the next page, but I just wanted to draw. This is what we're worried about: is how do you prove this theorem? And so that's going to be concerned with what proportion means. And in particular, I said this in terms of similar, but similar in Euclid is very explicit. Similar means equal areas and proportional sides. I mean, so this theorem sort of makes that a too strong a definition, but that's the way that he wrote it. And he doesn't say silly things about when I say similar, that was not his hypothesis. His hypothesis was, well, his hypothesis is these two sides, that these two lines are parallel. But that's essentially the same thing by the fifth postulate as saying the corresponding angles are equal. And that's the way we think of it today. But so there's a kind of a background question. There's things where I say, they say it this way, and we say it this way, and it doesn't make any difference. And there are other times when I say they say it this way and we say it this way, and something's really changed. All right, and so this is the definition. Well, that's what I was just saying about the two definitions of similar. Now, this was what I meant about another definition, or how else to represent proportion. It's what at least American students are taught by rote in 6th grade, that you cross multiply. And if you've done that, then as long as you know that you have that the segments have a multiplicative inverse, then this theorem works fine. So you don't have to have Archimedes. You do have to have division. So, the field over the rationals, or the plane over the rationals, is a perfectly good Euclidean style field. It did not need to have any kind of completeness, or Dedekind incompleteness, or now this is just a quick mention of what I'm not going to study. But the next 3 chapters in Euclid are the foundations of arithmetic, and things like proving the infinitely many primes, for example. And I made this distinction about not having the one, but this is the there's many definitions, including the one multiple, which is awkward because you're doing integers. Saying multiple is perfectly proper in studying the integers, but it doesn't mean that you can divide. Okay, and now we want to try to, part of this is we're trying to understand the difference in what axiomatics means in the 18th and 19th centuries, and Bolzano's questions are really very important in terms of shaping this. So Hilbert's geometry opens with, the following investigation is a new attempt to choose for geometry a simple and complete set of independent axioms, and to deduce from these the most important geometrical theorems in such a manner as to bring out as clearly as possible the significance of the different groups of axioms and the scope of the conclusions to be derived from individual axioms. So there's a couple of good questions here, like what is complete, and what is independence? Well, yes, I mean, he hasn't said independence. He says the significance of the different groups of axioms. And he's foreshadowing what he's going to prove is that the groups are independent in the sense that we talk about. He's not claiming, and it isn't true, that it's a totally independent set of axioms. It's that certain groups are independent from other groups. But what is complete going to mean? Oh, he did say independent, just up there. But what is a complete set of axioms here? Well, that's one answer, right? Yeah, everything, for every sentence, you can either prove it or its negation, right? And I don't think he actually knew in 1899 which he meant. The word categorical was invented, in fact, by John Dewey, but just in conversation with Huntington. They and E.H. Moore it's the American postulate school. I'll brag about the U.S. fluents. Really had the notion of isomorphism and categoricity pretty clear, but not the connection with completeness, but because that was muddled until Franco in the mid-20s. Okay, I guess we will go on with that. And now the question is, I'm trying to think about what completeness means. And I'm going to quote a little bit from Detlefsen about a particular notion of that. So Huntington said, or I guess Detlefsen's quoting Huntington, but miscellaneous collection of facts does not constitute a science. In order to reduce it to a science, the first step is to do what Euclid did in geometry. Select a small number of the given facts as axioms, and then show that all the other facts can be deduced from these axioms by methods of formal logic. Okay, but what's a fact? And Detlefsen gives us a very modern word, right? A data set. This is a collection of assertions. And the data set that you're trying to axiomatize are the things that everybody now knows is true. It's what we think it means, right? A local descriptive axiomatization is an attempt to deductively organize a data set of commonly accepted sentences. So Mick is taking a kind of a subjective sort of thing, commonly accepted, right? But it's part of what I've sort of based of what I've been talking about earlier. I say a concept is shared. That's this common acceptance. And the axioms are descriptively complete if all the elements in the data set are deducible from them. And they are modest if they don't extend the data set. By that I mean that you have some logic in which you formulate these axioms. And if from that you can prove lots of stuff that was not in the data set, that's immodest. And any kind of second order axiomatization is then automatically immodest, because it's going to tell us it's going to at least formulate the continuum hypothesis. There's just going to be all sorts of things going on that have little to do with the subject that you started with. So what we're looking for is a modest descriptive axiomatization for Euclid's geometry. Okay. Well, and so I had set this up for people to talk, and then I spoke and said. So I don't know, does anybody have any comment on this, or are we getting along? Yeah. So here I put this in because one of the distinctions, and it'll show up in what I do in a little bit later, is whether you are going to deal with circles or not. And Hilbert doesn't. Hartshorne does. And he does this by adding an axiom that two circles that are close enough together actually intersect in 2 points. And if the radii are not big enough so that that's possible. And that's called e.g. elementary geometry, as in by me, and I think it picked it up from somebody else. And in particular, we aren't going to know things like that it's the reals, or even the first order theory of the reals. So the claim is, here's a kind of, I should have had. Okay, I guess I've got a couple of pages later, but so elementary geometry includes the circle axiom, and HP5, Hilbert plane with the fifth postulate, is what Hilbert is using. And I'm going to now sketch something about getting the field. And so we're going to start with something that has, and I want to claim that it's descriptively complete. And a particularly nice way of saying this is a paper by Avogad, Dean, and Mama, maybe 10 years ago, who give up a proof system within a kind of a sequence calculus. And then their claim is, our proof system is sound and complete for the standard semantics of ruler and compass construction. So they claim we're going to reach all the, and they're descriptively complete exactly because ruler and custom, I don't know why I keep saying compass constructions are what Euclid is talking about. And here we have a proof system that gets them. So here, yeah, this is what I wanted to say a minute ago. What you have is the incidence axioms that I mentioned last time, and the connection axioms, which guarantee that the lines are dense linear orders. Some sort of triangle congruence axiom. I mean, you can, SAS, SSS. What's the one that's, well, anyhow, ASA, I guess, is right, but the other, and any one of those work. They're introducible on the earlier stuff, although Euclid is a little funny about that. He does one of them as a natural deduction from the other and doesn't for the other. There's some not the most precise or not the most modest connections. And either, well, so HP5 or the elementary geometry are modest complete for geometry of lines and areas, or one which has circles in it. And then if you want to get complete in the modern model-theoretic reason, meaning that what Louisa was saying, that every sentence is decidable or not, then you've got to tell us something about the field. And Tarski did it with a real closed field, but in fact, if you took, well, I don't know about the rationals, but with other fields, you can get such a situation if you, well, you have to know that the first order theory of the field is complete. I guess if I say add the first order theory of the field which sometimes I know the axioms for and sometimes I don't. All right, and then I say, yeah, and there's something I'm just skipping over here, that whether I'm talking about plane geometry or higher dimensional geometry is a real distinction, just one I'm not going to think about today. And you can't get a first order, I really want to say this, I don't think you can get a first order complete categorical theory of the, well, you can't. You can't get a first order categorical theory of the of geometry because of Lowenheim's Golem. All right, so now the next thing is to try to give some idea of these arguments of how the yeah.
In Tark's axiomatization, then you don't need, if you add the axioms for closed field,
yeah,
you don't need the connection axiom anymore, or you still need.
Oh well, I mean, yeah, I guess that's probably that's probably implied. I mean that they become redundant when I do that. I think that's right. Yeah. Okay, so what I want to do is just give some notion of this calculation with line segments, and I haven't read Descartes closely, so I'm not sure this is exactly what he's doing. It's pretty much, well, and I'm actually going to use Hartshorne's variation instead of Hilbert's, but you say, all right, what am I going to take for my numbers? And it has to be a congruence class of segments, that is. So you have a length. And then you define operations on those, both addition and multiplication. And then if you really want to do this, to make it be an operation on points rather than segments, you can say, I'm going to fix 0, and then the line segment 0A will be A. and then the operation becomes one on points. And that makes it a little easier to describe subtraction. So adding line segments is easy, right? You have 0 and AB, and you just say move 0B to AC, and that's the sum. And then 0C is the sum. And if we just are doing this with the positive segments, then we don't have subtraction. We don't have additive inverses, right? This is a semi-group, not a group. And so you have to do the, where did the chalk go here? You have to work with both sides and be careful about what addition means to get a... and for the moment, I'm just going to think about the positive. Right, and now, how are we going to define multiplication? Now, there's certainly different ways of doing this. I'm following what's in Hartshorne, and it's because it's a little different direction. If you what Euclid, what Hilbert says is, we use the theorems of Pappus and Desargues, and there's a whole line of geometries that, Desarguian means it's a division ring, Pappian means it's commutative. There's about 16 or 15 or 16 in this category. One of the things I did 30 years ago, not quite, no more, was prove that there's an Aleph 1 categorical plane, strongly minimal in fact, which is at the lowest level in this hierarchy. You just can't do much of anything. The idea was to get something that was non-Desarguian, And when I did this and then said, oh, how does it fit in this hierarchy? Oh, clear at the bottom. Now, I think I have the picture here. This is Hartshorne's picture, and it's showing that the multiplication depends on the angle that you put between the, if you fix the angle alpha, then similar triangles, sort of obviously that's what we want to have multiplication to mean. And I think the reason I chose this particular definition was because I was working also with a lot of this was being done for teachers, and well, that'll come in another page. So the question of multiplication is multiplication just repeated addition, and you want to be clear that that isn't true, right? If you take 3, that's fine. But if you want to multiply 5/3 or 5/4 by 27 halves, this ain't going to work. So you have to have made the definition of some sort of actually getting the field in order to make sense of this. And just a reminder that arithmetic is essentially undecidable while geometry is decidable. Right, and so now what I want to say something is about is something about the proof that these actions are associative and commutative. Now for addition, this is straightforward. Yeah, so this is the same thing that I said. Okay, so let me stop and so for addition, this is perfectly obvious, right? For multiplication, it's not. Neither the associativity nor the commutativity. And Hartshorne built it on something called the cyclic quadrilateral theorem, which, do I have the picture here? Yes. So the theorem is, if I have a quadrilateral, the vertices of the quadrilateral, not of A, lie on a circle if and only if angle EAC is equal to CDE. So let's go to that. EAC, if this angle equals this one, I think it is. Oops. EAC equals CDE. Yes, I had it right. If this angle is this one, that implies that they lie on a circle, and conversely, if it's on a circle and you draw that quadrilateral, you get those angles equal. And this is the kind of an argument that you can have in a high school geometry book, probably one that's in the book, not one you're asking the students to do. And then with it, you get the commutativity of multiplication. If you look at the part up here, you'll see that if you multiply up here, you get that EB is A times B, and if you multiply the other way, you get that it's BA. I guess I haven't. Yeah, it's BA if you do the multiplication down here, and AB if you do it up there. And so that's a geometric proof of the commutativity. Yeah, okay, so I'm not going to go through this in detail. I don't think we would get that much out of it. And then with that, you can prove the 6.2, the side splitter. But you consider this triangle, and we want to, and then we take a similar triangle, A prime, B prime, G prime. And, when we take B, we have A, B, C, and A prime, B prime, C prime that have these in-center built. So the in-center is the intersection of the angle bisectors. And then if you do this, the multiplication doesn't depend, is only depending on these angles. Remember that when I drew the picture for the multiplication, the crux was that they were similar triangles with the same angles. And so the cross multiplications will turn out to be equal. And you can do this in any of the three sides and you get the, okay, I mean, it's, and so the conclusion is that you get the commutativity. That will give you that when you look at the side splitter picture and then define the proportionality there, you get the you get the proportionality from the similarity. And there's nothing about Archimedean, there's nothing about limits. All there is this, that you've got this field structure. And it will in fact be the it's the normal multiplication, because on the rationals you've really sort of shown how to do it, and they're dense, so and the multiplication is continuous, so it extends to the reals. All right. And so these are the 2 points that we have used. The second one, that the area of the base, that this fact that the product of the base and the height doesn't depend on which side is chosen as base, is something that will show up again, and I think maybe I say a little more about it that second time. All right, so that's one edition of these slides ended up with saying this multiplication gives a good idea for the theory of area. It's online somewhere, I did it. But it turns out that there are harder issues here that arose in the late 19th century about the use of area. Do we really know what it means to have that the area is ordered? That in particular, if you have a square sitting inside a bigger square, does the smaller one have smaller area? And remember that when we went through book 2, what Euclid's argument was, if you have a triangle, it is equal complementable with a square. And so you would think, okay, I compare these two because I look at the lengths of the sides, and the one that has longer side has bigger area. And I think I'll have to change. Yeah, what I want to do now is switch to a different set of slides. This one will come back later in the lectures, but not today. Okay. All right. So I'm swapping over a little bit. Mostly I'm going to be talking about this issue of areas, but I'm now more of a model theorist. I've got these theories. I've given you first order axioms. We're going to talk about them in that normal way. But the question of whether saying two figures have equal area is explicitly definable in first order logic is a bit awkward, I think. I mean, And I'll explain why this is a problem. And maybe somebody will say, oh no, you've just missed this obvious point. But here we get into this distinction between explicit and implicit definition. And explicit definition is exactly what it says. You have this relation and there's a formula and it's a theorem that those two are equivalent. While implicit definition, you're expanding the language, well, you are in both cases, but all you know is that if you take two structures in the additional language that model the original theory and satisfy some formula about R, then the interpretation of R is the same. Yeah, if they depend on if the redux are the same, then the interpretation of R is the same. Now, this is GS is Giovanni, Giovannini, and Schimmer. Say it again. Schimmer. Yeah, that's right. Schimmer. Thank you. Yeah, and they have a fairly recent paper about the distinction between the notions of implicit and explicit, and in particular thinking of whether you have a specification of the meanings of the primitive terms, and then there's a lot of exegetical work here about what people have thought about this over time. So this is essentially Hilbert's claim, that I have given an implicit definition of the terms of geometry. And a sort of weaker claim is, well, I've given you a class of structures. And at least from a model-theoretic standpoint, the second one's just clear, right? That's what a theory is, or that's what the class of models of a theory is. But the other one needs some kind of argument about, how tightly do you have to describe this to make this make sense? And in particular, are there terms in this logic, have the various terms that we think we are specifying, right? I mean, now we aren't just specifying point and line. We're supposed to think we know what area is. And have we given a really explicit, have we really caught in a first order way the notion of area? And I guess when I started this and when I began writing these notes, I thought the answer was yes, and now I'm not sure. And I'll tell you why as we go along. Now remember that the frameworks were naive, we just sort of have a notion what model theory, what mathematicians do and what logicians do. And these issues really are, do we want to know this in the sense of what logicians do? Because we are talking about the formality of the definitions. And it seems to me that when Hartshorne, for instance, being the most modern clear source, when he says that he's basically done this, I mean, he doesn't make the philosophical argument, but it's implicit. He's in framework 2, right? And neither he nor Hilbert has a formal language. On the other hand, Hilbert, in Hilbert Bernays in the 30s, says these are first-order axioms, restricted first-order axioms. And, well, is it enough that the axioms are, do they really capture the concepts? That's the kind of problem we want to worry about. So here, well, that's what I was just saying. This is the remembering what framework 2 is and how it's distinguished from framework 3. because this is, defining geometry. This is what Hilbert's doing. But when I describe a topological space, once I get some continuity in here, we aren't really going to pretending that it's a first order definition. Topological model theory is something that people have worked on 3 or 4 times in my lifetime, and I don't think ever entirely satisfactory. So how do you compare areas? And I want to say 3 different ways of how you might say 2 things have the same area. Now, the first one is, I don't know, the physicist method, or the way people actually measure area. You cover by little squares. You have units, and you see how many are there, and then when your squares are too big, then you have to go to smaller squares, and then you have to go to smaller squares. So this is essentially a limiting process. There's definitely so that's something that a lot of mathematics is based on, and the people who are based on it that way just don't even think there's any other kind. And I think at some point I said, what would Newton think about such things? Well, he's when Newton and Leibniz are when you begin to think about it that way. And then there's a local method, as I call that, but it's by triangulating, some method of triangulation, and what you assign the area of the triangle is, so that you can do this in hyperbolic geometry based on something called the defect, which I knew what I meant when I wrote this, but don't know right now. But it's all in Hartshorne. And then I'm calling this the representative method. I mean basically what Euclid is doing, that it's an equivalence. 2 things are equal areas if they're in the same equivalence class. And so Hilbert gives a general definition that applies directly to the first 2. An area function is a function from figures to some ordered semigroup. Because the congruent figures have the same area, and the area of 2 intersection areas is the area of 2 intersecting figures is the sum. And ordered semigroup word hadn't been invented yet, so Hilbert doesn't say that, but he knows very well what he's doing. But now, the way Hartshorne organizes his book is he writes down, he says, Hilbert introduced this notion of equal content, and this is what it means. It's an equivalence relation such that congruent figures have equal content. Disjoint unions of figures with equal content have equal content. Actually, pause to think about this a little bit. Is there anything here that seems a little funny? Yes. Okay, that's one. I think it comes up. Well, it's because in somewhere in one of these arguments, it's exactly that the triangle you separate is half the area of the. You draw the diagonal of a square and both sides. Yeah. Right, and yes, that I think is the real issue, and in fact, Hartshorne will prove that these 2 are basically equivalent. and the halves sort of falls away. I think maybe another reason is that there are some, as I say, there are some specific propositions that use halves, and then Hartshorne has some counterexamples if you are, you know, why this is. Okay, and then, so this is an implicit definition, right? This is saying, here are properties we'd like to have of this relation. If I can find something that satisfies those conditions, then I have an implicit definition. There's something wrong with what I just said. Do you know what it was? We have this list of conditions. Where are they? Right, but also we have to have these things defined, right?
Yeah, you have to have the other things defined, yeah.
Yeah, and so you have to be able to whatever you're spelling out for equal content, you're going to have to be able to describe those things in first order. And that's going to be an issue. You see, this is, so I've put in here this thing about n figures, that to say, oh, well, I'll fix this by have a separate rule for things that are things of n, that are unions of n triangles. But that isn't good enough, because certainly an n triangle and an m triangle can have equal content. The triangles are smaller. And how long a list I need, and how many, you know, if I'm dealing with a polygon, for a mathematician, a polygon, you can quantify over polygons, but in first order, you can say something about, you can have a schema of n-gons, but you can't have, and so it's all right if we turn to a schema and do it carefully, but it's a step that has to be made. Now, I want to go back to I think we had this picture very early on. This is the proof that parallelograms on the same base and in the same parallels have equal area. And we want to make clear that this is about equicomplementability, not equidecomposability. So suppose that this is a non-Archimedean field. And these 2 points are out at infinity. Now, the claim is that they have the same area, and you are supposed to do that because you subtract this triangle and this triangle, and you get things that are equidecomposable. But they can't be, because this has infinite length. And what is finite? Oh yeah, this parallelogram has finite sides, and this one has one infinite side. So there can't be any decomposition going on here, and that's built into the equicomplementability at some point. So, oh no, I mean the claim is this theorem works for equicomplementability. It does not work for equidecomposability, because this parallelogram is not equidecomposable with this one, because you can't cover up the sides of this line. And so this comes down to Desolt's axiom. Now, Desolt is somebody in the 1870s or so who is, who plays a big role in this, but that's about what nobody knows about him, at least me. And he phrased the question as, if a polygon is divided into parts in a given way, it is not possible when one of these parts is omitted to recompose the remaining parts in such a way that they cover entirely the polygon. I mean, it seems obvious, and yet it's quite clear now, and the result is justly well known for, at least in certain circles, for realizing that ain't obvious. And Hartshorne's version, if a figure Q is contained in another figure, and if the difference has non-empty interior, then P and Q do not have equal content. And it's the not equal, it's the not of this that's the essential issue, as I'll describe in a minute. And so here's I've just quoted Hartshorne's phrasing of these problems. I'm not going to use greater or lesser because we don't know what that means yet. And we can get it if we have Z is the Zolt's postulate or whatever. And then the question is, I do not know of any geometric proof of the Zolt's axiom from the theory of content. And that I'm pretty sure is open. I mean, I certainly don't know how to answer it. But even more, is there a way of maybe if I enlarge the logic, I can get a hold of this. All right, so are there any comments about this from anyone? Are we?
I imagine he's not wanting to use the field theory.
Yeah, or at least
Some specific.
yeah. I mean, I think that's basically what he's about. I guess conceivably it might say it's okay to do the coordinatization, but then somehow the way you divided up the way when you defined equal complementability, then you escaped. But I don't know. That seems like the more geometric part of the issue. So, but I think that's the kind of issue he means. And the framework issue is, what really what I'm willing to believe is that in framework 2, Hartshorne and Hilbert have an argument, but it isn't really answering the question, because the question makes sense when you talk about formal. And I'm going to do a little bit with L omega 1 omega, so that's why I said what logic. But yeah. So here again is just probably what I've just said, but in a little more precise way. There's a hidden quantifier over the number of triangles, right? A figure, it's a subset, can be written as, but how many? And the essential problem is, if you want this to be an equivalence relation, the how many is unbounded. Because you take two things and you want to say, now I can find something that matches, that goes clear across to the third. And this involves refining the two decompositions that you have, and in a way that, as far as I can tell, is not bounded. I mean, it may be that it is, and actually I say something a little bit later about maybe Hilbert knows how to bound it and didn't write it very well. And now if we try to go into a language, we can do something like, if I have a formula which has, if I'm worrying about a figure with n vertices, then with 3n, I have 3n parameters, and I just write down about these 3n sets that they make up a figure, that I have disjoint triangles. Or, and I'm probably do this on the next page, I can be a little more detailed and write a formula in 3 variables and a free variable x, which says x is in the interior of this figure. Right? It's either on the circle, it's on one of the triangles, or it's in the interior of one of the triangles. So that's somehow getting closer to our notion of what the area is, and it's essential, because when you make these definitions, you're going to switch to different. You're going to say that this 17 area, the decomposition has the same area as this 27 area, 27, and why are they the same? Well, because the same points are covered, and you can formalize that, but is it enough? All right, and so here's the formal definition of equicomplementable. First, equidecomposable. Just simply you have the scissors congruent is what they say in the United States. Do you use that phrase here? Scissors is this little thing you cut paper with, and so it means you can cut up the pieces of paper and rearrange them. And so that's the jargon in the grade school texts, or maybe I really mean high school. And then equicomplementable. P and Q are equicomplementable if first I can find a Q, so this is P and P prime, and I find a Q and a Q prime, and these guys are scissors congruent. And this union this is scissors congruent with this union this. I haven't actually said anything about what's going on in P and P prime. I mean, I've said something about what's, but not how they compare. I compare the Q and the Q prime and the P union Q with the P. And if you think about it a little bit, this is what actually happens in that diagram for the two triangles, two parallelograms on the same. I didn't touch the actual parallelograms. I subtracted them from different sets. And of course, this is the right notion. I mean, this is clearly what Euclid is intending. But we have this same problem about describing this. Right. So where it is, and I say I can do it in L omega 1 omega by. So. This is what I mentioned a minute ago, talking about what's actually the area covered by this collection of triangles. And then they are M equidecomposable if you have, you take this one and take that one, and then you have the, these, this one is, yeah, these two are equidecomposable, and this one is another name for the first one, and this is another name for the second one. And so I've switched to getting the same number of points by, and yeah. And so I can say something I call that theta nm. And it won't surprise me if I just stopped here, because no good. Then they're MR equicomplementable if you can find for each M and R, you get an M things that will handle the first half of what I did yet before, and then the R is telling you about the P and Q. So the M and the R are the two sizes of decompositions that I have to put together. And so I can write all this down, and for any particular M and R, I can write down a first order formula. But saying you're equidecomposable means you take your little A bar and A bar prime that define the first one, and somewhere in the infinite disjunction over the M's and R's, you get a solution. And you get it. So I mean, and this in a positive direction, this isn't too bad. When you give me something that are equidecomposable, it happens because somewhere at some finite stage that happened. But if you want to say, as in the conclusion of Hartshorne's Desolt's principle, it's not equidecomposable. You're now asking for an infinite conjunction. You've got to check all these cases. So this was a brainstorm that doesn't seem to work. And this is exactly what I'm saying. And I want to say something about, we get this in, we want to talk about this in terms of the area function. That's because another thing. In the middle of this theorem, you need to know that the area of the triangle doesn't depend on which piece is given as the base, and this is something that Andreas worked out, but I don't think it's really what we want here. Here is the thing that's kind of interesting. So there is a man named Gua, who is not a mathematician, maybe an engineer or a physicist, I don't remember exactly, but also interested in education, I think, which is why he's done this. And he has a paper that has come out fairly recently, where he says, I'm going to avoid this second order issue with Birkhoff by having a two-sorted system for the plane and the field, and write down first order axioms for both of them. In particular, distance is saying that there's a function d from pairs of the point elements to the field that's a metric. And so he sort of says you don't have to worry about area. You get trouble here when you start talking about the Pythagorean theorem, because every ninth grader knows that the Pythagorean theorem is a squared plus b squared equals c squared. It ain't got nothing to do with area. Okay, I mean that's a correct observation about high school students. But then he works from Tarski's axiom system, and then notes some interesting comments of Tarski. Well, so this is what part of the content of the elements is not formalized in E2. Okay, so E is elementary geometry. Tarski's more or less equivalent to what we've talked about. And E2 is extending it by weak second order logic. You allow quantification over finite sets. But even in E2, there's no notion of area. Not even for polygons. And in addition, modern mathematics, area is a function from sets of points, right? You're talking about the interior. It's some set of points, and there's no sets of points in first order logic. I mean, I figured out a way to do it a minute ago. Right? It wasn't very there. It's not that there are none, but it takes some definition. And E2, the 2 is, so he doesn't want very much set theory, so he has only. And well, but why shouldn't we be able to formalize it as in Hilbert? And I guess I wrote this a week ago, and now I'm saying, well, how do I really believe that Hilbert did it? Yeah, so this is what, oh, no, I'm sorry, E2 was the, I'm sorry, I've got it wrong. E2 is just, the 2 is for the plane, and then the prime is when he goes to second order logic. That's a weak second order. Right. Okay, and this is Tarski's elementary geometries paper. But then, while Tarski's theory of area is non-numerical, dealing with equidecomposable and equicomplementable relations only, we may have a theory of area in the numerical form, and so he's referring to Hartshorne's thing. However, an area function that assigns a number to each polygon is a set function, which cannot be part of a first-order language similar to the language of what I was doing on the previous page was partially disagreeing with that, but not. I mean, yeah, I can tell you how to define some set functions if you can do it uniformly enough, but I don't know if I can do it uniformly enough. And so this is another way of phrasing Goua's problem. And I thought it was nice enough to call it his dilemma. In a Hilbert plane, there is an area function, but see, Hilbert is getting this area function working in framework 2. And it works fine, right? But in framework 2. And then he's saying, well, but this formulation certainly doesn't make sense as a function that's going to be a first-order function, a function of infinite many variables. That's the real issue. And now, what this is not, well, I think when I wrote it, it was supposed to be, these are the solutions, but it's, here are ways you might go at it, and some of them work and some of them we aren't sure about. Well, no, well, yeah. So you might say, is there an implicit definition of equal content? And the problem is that this equal content is not a finitary relation. And even saying maybe equal content between an n-gon and a 17-gon. We can try to give a definition of that, but we're going to get into trouble in doing that because of the length of the triangulations. And if you can give formulations, then you can give what I call, well, Platy-Blanchette calls the semantic methods of proof, and I'll say something about that in just a minute. Or trying to do it in Rodrigo's format, or trying to work in L omega 1 omega, or trying to treat equal decomposability or equal complementability as an implicit definition. That was what I was thinking of when I wrote that down before, but the problem was that the notion didn't show up to be a finite set. And then Goua does give an answer with the two-sorted thing that I think actually works. I don't it, but you. I don't know. I have to think about what his alpha is, because what's the domain of alpha? Why is that actually a definable? And Birkhoff, I think, is also mathematically fine, but basically, I think this works in framework 2 and by various ways, but whether it actually works in framework 3 is a real problem. And see this, yeah. So this, I think, what I say here is right, but it only does half the problem. If I'm going to let script f sub n be the figures on that are unions of n disjoint triangles, and then you add a 3-n-ary function symbol that tells you that any figure in Fn with verticals a bar, alpha of a bar is the sum of the areas of the. So this is the natural notion of an area function, but it's a schema because you're restricting to formulas which are to areas which are the union of n disjoint polygons. And then you have this problem. Suppose you have a figure P that's in both Fn and Fm. How do you know that alpha n of it is equal to alpha of m of it? Right, and so that's the, let's see, can we write something like, for every x of length 3n, alpha n of x equals alpha m of y bar, and I should have had the quantifiers out in front. Implies what, I don't know, and now I need some statement about equal complementability to make sense of this. Now, what Hilbert does is argues about finding the refining decomposition so that you know that you get, well, the theorem is any decomposition of the same triangle gives you the same value. And the difficulty with it is how do you say that when you have to have more and more elements? And when I was looking at it 2 hours ago, I guess, and in Hilbert, he writes, oh yes, I was just going to pull up the Hilbert thing here. Yeah, I must be just about out of time, but no, here. Yes. Come on. Shouldn't it be Control L? What? Okay, I don't know why I'm Shift L? No. What's the command for full screen? Control L, right? Well, it worked every other time today, but not today. Oh, okay, good. All right. So he starts at the beginning. For each of the triangles, this is yes. It's this point about having a transversal decomposition. Transversal decomposition is a particular way. The lines have to come. You can't. Maybe yeah. It's defined down here. So, well, I think that just for now, you in particular, one side of the triangle can't be split by in the lines that draw that make the decomposition, and there's conditions like that. And I think maybe one rescues this by saying at the beginning, ideal only with transversal decompositions, and then maybe this works. And that's certainly a plausible explanation. I just haven't had enough chance to think about it. And Hilbert isn't each of the triangles, the decomposition into it is reducible to transversal decompositions. I don't think he is really trying to prove that. He's saying that's clear, and it isn't at all clear to me. But saying that you restrict to those, that's certainly an approach. So it is. Well, I've got 4 minutes. Does anybody want to say anything, or do I want to say anything? What do I have in the notes? Yeah, well, at one point I wanted to say I had an explicit proof in L omega 1 omega, but I'm not sure of that. And even if I did, what I'd get out of it, I can use Beth's theorem in L omega 1 omega and get a L omega 1 omega definition. It doesn't give me a first order definition. Oh, so let me say something about this business, that method of semantic proof. So this is in Hilbert and Ackerman, and it's in the 38 edition, so it's that they knew what the completeness meant by then. I was thinking about this, could not have been in the first edition. So far we have used the predicate calculus only for deducing valid formulas. The premises of our deductions were themselves of a purely logical nature. Now we shall illustrate by a few examples the general methods of formal derivation in the predicate calculus. It is now a question of deriving the consequences from any premises whatsoever, no longer of a purely logical nature. So he says, let's give ourselves some axioms for a first-order theory, and if we prove something from the hypotheses of this in this theory, and the thing we're proving is some sentence, then by Gödel's theorem, your proofs are finite. You have actually a proof of the result. And so this is, I think, a general argument that model theorists will write every 3 or 4 papers at least. Now this is a theorem of such and such a theory, when they've never mentioned proof anywhere. There's no syntactical proofs, but they've given proofs using higher order methods that a certain proposition, which is expressible in first-order logic, is true in every model of this theory, and then Gödel tells us there's a proof. And that's what I picked up the notation from Patty Blanchette, who said that's the method of semantic proof. Well, that's the point. I want to say it is in this sense that Hilbert and Hartshorne proved result in HP5, but I'm not convinced of it as, like I was 2 or 3 days ago when I wrote that. And I think, let's just quit here. That was the last thing I said. So, all right, so I'll stop, and any questions are certainly welcome.
Questions, comments?
About the two-sorted framework of Google, the other sort is made by finite sets of points.
One set, the one sort is points with axioms of Auditório, and the second is points which are the models of an algebra of a real closed field, as in Tarski.
He introduces the field there.
Yeah.
But it will not work for categoricity, but we could introduce another two-sort framework like that. We have points and we have finite sets of points also. It is the first-order reduction of weak second-order logic. It will not work for categoricity, but you have a first-order framework, and maybe some proofs can be recovered in this way. But
I don't know. I mean, what Tarski said was that he couldn't express area in the weak second-order version of his. So that seems. I mean, it seems like you're doing something less strong than that. So,
less strong than that. And weak second order logic is also interpretable in omega logic.
Okay, so yeah.
And also in L omega 1 omega. So
Oh yeah, I guess.
yeah,
Oh yeah, I see. Yeah,
yeah.
right, yeah.
The existential.
Yeah, right. It's the disjunction. Yeah, right. Yes, right.
And
Okay.
also in omega
Yeah,
logic,
right.
it is omega projected.
Right.
Questions, comments to Professor Baldwin? Oh,
Yeah.
thank you again.
Thank you.
with the second lecture of Professor Rodrigo Freire on mathematical defining. Thank you, Rodrigo.
Thank you. We have already seen some things, and yeah, I think that I will start from this point. So I am basically proposing that mathematical definitions must be formally conceived as implicit definitions omega logic. It's a short, long story short, is that mathematical definitions are best understood as omega logic definitions, and this has to do with this very basic mathematical notion, which is in a sense undefinable, and that is the notion that I'm calling the standard natural numbers. Well, we have discussed a lot of philosophical issues. There are many more behind this conception, but I think today we will go a bit faster towards the development of the theory, right? So when I say that a definition or mathematical definitions are better understood in terms of implicit definitions or as an interpretative activity, I am saying roughly that a definition of a predicate is the identification of the interpretation of the predicate. Basically, this notion of singling out an interpretation of a predicate. And so we have this issue of what are the possible interpretations of a predicate, right? And since a predicate is always defined within a defining theory, the interpretations of the predicate are always a part of the interpretation of the theory. So we must discuss what can count as an interpretation of the theory in order to answer this question. And this leads us to these two issues that must be addressed. What is an interpretation of a theory defining a mathematical predicate, and which ones are the right interpretations, right? Which we usually call the models of the theory, the interpretations that correctly interpret the theory. I will consider two options, but there may be many more, right? So as I have said, there's nothing in the symbolism that tells us how are we supposed to interpret them. This is part of our meta-linguistic agreements, basic agreements on semantics. This is not particularly related to mathematics, right, or mathematical practice, right? The linguistic practice also has the same kind of structure, right? We have the oral practice of language, and then we started writing down, right? We somehow invented the writing, or discovered the writing, doesn't matter. But there is nothing in the written language that fixes how we are supposed to interpret it. So these interpretations are based on agreements, right? Common ground, right? Language is common, is shared by us. So the interpretation must live in a common ground, what I am calling the basic semantic agreements of our language, right? In particularly, mathematical language has the same kind of structure. And so, how are we supposed to interpret a mathematical language? So there is this standard Tarskian semantics, right? Now, for at least classical objectual interpretation of quantifiers, Tarskian, Robinsonian. There is also before Tarski and Robinson, Skolem and Gödel. When Gödel proved the completeness theorem, there was no Tarskian semantics yet. He used Skolem function-based semantics, right? Semantics based on Skolem functions. So there is also this kind of semantics, but the Tarskian style semantics became standard, and this is one basic semantic agreement that we have. We shall interpret our formal language in Tarskian terms. But this does not solves everything, because we still have to say what class of structures are admissible. So it is usual in first order logic, and now I think I will address partly the question made by Diogo yesterday. In standard first order logic, we usually, the usual agreement is that we consider only non-empty general first order structures, but all non-empty general first order structures. Well, of course, a trivial way to consider another class is to consider all first order structures, including the empty one. So this leads us to something like the inclusive logic, right? We have a problem with free variables, but if we stick to just closed formulas, sentences, we can formulate perfectly good first order logic, which is valid also for the empty structure, right? But also, instead of expanding the universe of structures, we can consider other structures. The first order structures are the classical ones. You can also extend the universe considering non-classical first-order structures with predicates which do not satisfy, for example, the excluded middle or something like that. But sticking to classical and non-empty first-order structures, we could also reduce the class, consider a more restricted class in some sense, and this leads us to the to our preferred interpretative basis, which is what I'm calling an omega logic based semantics, right? It is the class of omega structures. So we have Tarskian semantics, everything just as usual, first order language, but expanded with some symbols for the standard natural numbers. And we have this, the only difference is that we have now only the omega structures as the admissible ones.
There is a binary relation in the language that satisfies the axioms of the CFC. Is that right? And then you may add further.
Yeah, it will work in general for any kind of theory, but I am considering these extensions of ZFC. Yeah. So how things work in both interpretative bases, right? So we are now considering these questions. So what is an interpretation of a theory defining a mathematical predicate, and which ones are admissible? So the interpretations in the first interpretative basis, the interpretations of defining theory are just as usual, the usual agreement, non-empty first order structures, and the admissible ones are just the models of T. The correct interpretations of T are the models of T, right? This is the usual agreement. And now answering Diogo, I think if we stick to this, we have first order logic, right? It says the semantic layer is just first order logic, and the syntactical layer is first order for both approaches. And so if we define logic as first order logic, this is logic. Right? And my thesis is that mathematics is different in that mathematics is omega logic semantically. Right? Mathematics assume the basic agreement behind mathematics assume the natural numbers, standard natural numbers. That's a separation that we may draw. So if logic is first order logic, then mathematics is omega logic, and these things are different. So answering what you have asked. So now in the first interpretative basis, we are given a structure which is a domain of individuals and extensions. Let us think of sets, right? You may think of R as unary to simplify. So the structure contains a domain of individuals and subsets of individuals, which are these RA And these subsets are such that when you take a subset and its complement, then it gives you the whole domain, and the intersection of the subset with its complement is empty. So this is a classical first order structure. The individuals admit identity, which is as usual, so in a classical setting. And in this case, we say that T defines the predicate R implicitly in terms of the other predicates and with respect to the class of all first order structures, if and only if RA is the only set of tuples, right? Appropriate tuples in A that can be assigned to R to generate a model of T. Professor Baldwin gave the complete definition. That the idea is that you cannot change this. We have the structure A. You cannot make any change on the interpretation of R, keeping the rest of the structure unchanged, and get another model of T. It is impossible to change just this part and still have a model of T.
It's not that it's a sequence of tuples that generate the model in the sense that there's some function symbols in the language that give you all the other elements. Your notion of generate is something like readout.
Generate, yeah. Generate here means just that take RA and put another thing in its place. Generate just in this sense that not a cumulative generation, but just take the predicate RA out of A and then put another one in its place. Yeah.
It is the usual notion of implicit definition.
Yeah, it is the usual notion, yeah. And then we have this result that I will try to show in the lectures, that to be implicitly defined over the class of all first order structures is equivalent to be explicitly definable by a first order formula, right? A single formula by Beth's definability theorem. And therefore, in this setting, we have the undefinability of these notions, right? So the truth predicate is undefinable, and the notion of definition is undefinable, and the notion of standard natural number is undefinable. I will say something about that. And maybe also other mathematical notions, as we have interestingly seen the notion of area in elementary geometry, maybe is also one of these examples. So our preferred interpretative basis is constituted by the class of all omega structures, right? So this is what I have answered, that this could provide the dividing line between at least first order logic and mathematics. So mathematicians assume or agree that they can unequivocally select an instance of the standard domain of natural numbers, it is always available to them, and it is a basic selection, not reducible to simpler definitions, right?
Yeah, I'm getting, when you say that, suppose I'm thinking about the theory of algebraic closed fields, right? Then the natural numbers are not there.
Yeah, but they are there as, for example, the degrees of the polynomials. They are meta. If they are not really present there, they are theoretically, they are at least meta-theoretically. So you have to say that a field is algebraically closed, you must say that for any degree, a positive degree, you have a root for the polynomial. There are other ways in which the natural numbers are there. For example, you might want to say what is the characteristic of the field. So if it is zero characteristic, what do we mean by this? So it is a schema. It is exactly the standard natural numbers. You say 1 is not 0. 1 plus 1 is not 0. 1 plus 1 plus 1 is not 0. It is exactly that kind of iteration process that we agree to have in common, to have shared. So it is not there theoretically, right? But it is available to them when you do inductive constructions in the
in the meta language. I mean, this seems to be the point that you're saying that the natural numbers are there in the meta language. You're using it to describe it. But in places where we, know the natural numbers are not definable in the structure, and even, maybe you can pick out, you can say you take an element A and you have A plus A and so on, but whether that's 1 or not, that'll depend on my having, if I say it's the identity of a field, the multiplicative identity, then probably you're going to call it 1, but
yeah, but 1 here has no intrinsic nature. It is to be a standard natural number is to be named by a numeral. So anything that is named by a numeral can count as an instance, what I'm calling an instance of the standard domain of natural numbers. So this 1, 1 plus 1, 1 plus 1 plus 1, and characteristic 0 fields are indeed constitute an instance of the standard domain of natural numbers, even if you don't want to distinguish this collection. And but my point is, I am considering mathematics as a whole, in the sense that even if you are interested in algebraically closed fields, you as a mathematician, or for example, a group theorist is not a person that proves theorems in first order group theory. He proves theorems about subgroups, normal quotients, and stuff like that in set theory. So the same thing about algebraically closed fields. You prove, for example, the categoricity, a field theorist, let us say, proves theorems about categoricity of transcendental bases of stuff like that, or non-categoricity in Aleph 0 in set theory, usually. So I am concerned with this this framework in which all local mathematical theories, a local mathematical theories is a set of concepts and theorems, let us say informally, that is formulated within set theory in this sense. And in this case, the natural numbers are basically always there. When you are dealing with groups, you will consider the order of elements or index of subgroups, inductive constructions with natural numbers, generated subgroups or chains of groups. So it is in this this sense of, there are two senses of group theory or theory of groups. We have theory of groups in the sense that theory of the class of groups in set theory, or the theory of groups, the first order theory of groups. So I am concerned with the first sense. So so axiomatic mathematics in this sense usually presuppose the possibility of defining an instance of a standard domain of natural numbers as a starting point for its practices. And I am saying that this is a basic agreement. I would like to remind you that this it is not the case that we have an infinite agreement, but that we agree on the process of iteration itself. We agree on how to continue from an arbitrary point, right? And this is not an intuition, a mental object, or it is an agreement, that it is something that we have in common. So a basic mathematical notion is an agreement like that, a semantic agreement, just like a basic notion in general in language. It is an agreement on communication, right? How can we have, we were discussing before the lecture, how can we have the same language all over the country? You travel 1,000 miles and still can communicate, right? Because we share a set of sometimes implicit rules, right? That implicit agreements on how to understand what is said. So it is the same with mathematics. Oh, but I am speaking about the standard domain of natural numbers. What is it? So an instance, right? There are many instances. There is no, I am not claiming that there is the standard natural numbers, right? But it is a mathematical notion that is, it has many instances. An instance of the standard domain of natural numbers is just a domain whose elements are denoted by a sequence of distinct names, such as this. So we, the important thing here is basically are the primes, right? We, this is where our agreement is. We agree on how to iterate the primes. So pick an arbitrary point here, and we agree on how to continue from that point on.
Let me just try. Is it that this domain sits there on the side. It's used in the practice. I mean, the last line of the previous thing about the successors are a starting point for its practices.
Yeah.
But it's not part of the structure that I'm studying as a mathematician, where there may very well be no definable sequences. I have a theory of rational order.
Theory of
Rational order. The real rational numbers, dense linear order.
dense linear order. Yeah.
There's no successor sitting in there.
Yeah.
It's just that you have made it available for me to talk about that.
No. I am making it available to talk in what we would call the meta theory of this.
Yeah.
If you are, it is that difference that I mentioned. If you are taking the first order theory of dense linear orderings, then there are no natural numbers there as theoretical entities. They are there meta-theoretically, right? But what I say is that mathematicians usually think of themselves not as living inside the first order theory of dense linear orderings. They think of themselves or of their practices as living in the set theory. So they do not restrict themselves to that small first order theory, but to set theory. It is a set theory that is identified with the set of rules they must follow. So you can, of course, investigate the first order theory of groups or whatever if you wish, but you usually will do that investigation within theory, and it is not identified with the set of rules, basic rules you must follow.
So does this mean that if I do want to study dense linear order, I work in ZFCN, and in ZFCN I define the theory of dense linear order the way I would anyhow, and the change here is that that you've made clear that this is a well-founded model. I'm only dealing with well-founded models of ZFC when I study.
Yeah, that's more or less like this. It makes no difference for the theory of dense linear orderings. So you define this class of structures and you study it in the same way within set theory, but in the interpretation, right? Interpretative layer, you have a distinguished instance, always a distinguished instance of the standard natural numbers. That is, the models of set theory are what you were calling not necessarily well-founded, but that they have an instance of this structure there to be used if you wish. If you don't wish to use but it is available. That's the point. It is available to them. The standardness of the standard domain, so defined, rests on the matching of its individuals with the names, the sequence of names. This is to be the standard domain of natural numbers. That is, an ambiguous selection of such a class of domains is possible once mathematicians agree in their practices primarily on what could count as a sequence of symbols in a language. If we cannot agree on this, we cannot agree on what our first order theories are, for example. And secondly, on whether a sequence of symbols could be used to select the domains whose individuals are parameterized by its terms. That is, if we can agree on the naming schema, right? Whether a sequence of symbols, a sequence of names could be used to point to the domains, right, whose individuals are named by those symbols. Right. Here I'm saying that a part of this agreement can be taken for granted. Right. If we don't agree on what could count as a sequence of names, if we don't agree on what is the iteration process itself, we cannot agree on what is ZFC itself or any other first order framework. So, well, I have already corrected some of this. John has pointed me some stuff, but informally, an omega structure is just a formal first order structure expanded with a domain of standard natural numbers, an instance of the domain of standard natural numbers. So we have all first order structures can be also immersed in an omega structure. So they are in a sense more restrictive. So it is a subclass of the class of all first order structures when you look at the class of all first order structures for the full signature. But if you look from the point of view of the smaller signature, then all first order structure can also be immersed in an omega structure. So it is in a sense also an expansion of the universe. So we have this. So let us consider this. Instead of considering only general first order structures, we consider structures that alongside with the structure we have the natural numbers there as an appendix. The natural numbers, there's an instance of the standard domain of natural numbers are appended to our structures now, to be used if we wish. We can forget about it and it's just okay. But it can be used if necessary. And there are many cases in which whenever you are doing some inductive construction, for example, auxiliary construction like that on polynomials, or on you were in a group considering A to N to consider the order of the elements and stuff like that, you are using this auxiliary domain. So the important thing is now that this notion of standard natural number can interact with other notions. So we may, for example, reformulate set theory using this this notion, and we have this new theory, ZFCN. ZFCN is not, from a point of view, very different from ZFC, right? It could be equivalent to ZFC in the sense of being a usual definitional extension of ZFC in the first order setting. So ZFC n is obtained from ZFC by the following additional symbols. We have n, and a sequence C0, C1, C2. Of course, also the process of iteration is implicit here in the numbers, which are all unary predicates. They are names, proper names, right? The idea is that this is the name of 0, this is the name of 1, this is the name of 2. So the additional axioms of this theory says that n denotes the property of being a finite von Neumann ordinal, and the names denote the usual finite von Neumann ordinals, right? So C0 denotes the empty set, C1 denotes the unitary set of the empty set, and so on. So this theory can be interpreted in the class of all first order structures, and then it is basically equivalent to ZFC. That is, n is the least, the difference that I have written yesterday. So C0 is basically the empty set, C1 when interpreted, right? So but I will write this this way. C1 is like this, C2 is like this, and we agree on how to continue this sequence for any arbitrary point. So we have a schema here, and we have n equals to the smallest inductive set in the usual sense. Is this set just this? Right? The question is if this equals to this. So in omega logic, we force this to be the case. We force this equality. Oh, so it is impossible to have a non-standard number here? No, you can take the ultra product of this, some ultra power of this structure, and you will have the non-standard numbers. But not here. Not inside this this set, right? That is the proposal, right? Things can be done differently also, but this is if we interpret this theory in general first order semantics, there is no guarantee that these things are equal. One example is very interesting, is that non-standard set theory IST from Nelson, in which we have omega, and we have the standard elements of omega, which do not constitute a set, right? So in this set theory, we could, for example, equate this to this, but this omega logic, instead of identifying this set with this set, we would identify this set with this set. But this would also require omega logic. First order logic is just not capable of saying that even this is equal to this. The standard natural numbers in IST need not be this. So well, what difference does this make? I will give some examples, but let us now come back to our general notion of definition. So, so suppose that we are in this theory. This is our background theory, and now the semantics of this theory is omega logic semantics. What is a definition in this framework, right? So my proposal is that the primary definitional notion is the notion of implicit definition, which is the following. So let us take the general notion of implicit definition with respect to a class of structures K. So we say that a set of first order sentences T, a theory, implicitly defines some predicates denoted by P, Q, R, so on. Maybe finite, maybe only one. In terms of the other predicates and with respect to or over the class of structures. K is a class of structures for the signature of T, right? If and only if for each A in K, right? So we consider now only structures in K, which is a model of T. The extensions PA, QA, RA, and so on are the only interpretations of P, Q, R that can be added to the reduct of A to obtain a structure in K which models T. So T implicitly defines these predicates P, Q, R if in each model of T, which is in K, we have that condition that we cannot change the implicitly defined predicates to obtain another model. If we change these predicates and keep the remaining ones invariant, then the resulting structure is no longer a model of T. So that's it. It is a way of saying that these extensions PA, QA, RA are the only ones that are compatible, the only ones that we can have in A that are compatible with T. So that is what this is saying. This means that PA, QA, RA are unequivocally determined among the models of T which are in K. by the other predicates. Right? We say that T is the defining theory for P, Q, R, which denote the defined predicates. So let us consider an example. Let T be the extension of our base theory ZFCN obtained by the addition of the property symbol S. S stands for standard. So we are defining a predicate of just like this one. Right? So this is just a symbolic extension, right? And then we should consider the difference in semantics that we have in this theory. So we have this ZFCN, and then we add the property symbol S, which says that S is included in N. So S is a subset of N. And moreover, S contains 0, 1, 2, etc. So what is S? S is something that lives in between this and this, right? S is somewhere in the midway between this and this. This is S. So that's impossible. They are equal. No. They are equal under the semantic agreement of omega logic. They are not equal in the standard first order semantics. This equality.
The two things that you're comparing are N and you're saying one. You're comparing two sets, and I'm not sure what they are.
S and N.
Right, and S is whatever satisfies this condition.
Yeah.
Right, and by the first axiom, it's a subset of N.
S is S is in between these guys, this set, which may not be a set in depending on your semantics. In IST, this is not a set, for example, right? Because otherwise it would be inductive and smaller than this. So it is in between this and N. So this theory T obtained in this way, it is ZFCN plus these axioms, right? Plus S and plus these conditions. S is not implicitly defined in the first order semantics, but it is implicitly defined in the omega logic semantics, right? So T implicitly defines the property S in terms of the other predicates, these other predicates, and with respect to the class of all omega structures. It is a well-known consequence of the compactness theorem that T does not define this property implicitly in terms of the other predicates and over the class of all first-order structures. That is, we have this general notion of implicit definition relative to K. If we change K, an implicit definition may cease to be a definition. So this is an implicit definition when K is taken to be the class of omega structures, and is not an implicit definition when K is taken to be the class of all general first order structures. So we have more definitions in the omega logic setting, more implicit definitions. But we have Beth's theorem. So Beth's theorem says that in the general first order setting, the general first order semantics, implicit definitions are equivalent to explicit ones. So this means that there is no explicit, oh no, this is not what I said, but we have more implicit definitions in the omega logic setting, and so we can have some definitions which are not explicitly definable in the previous sense anymore. So this S turns out to be also explicitly defined because it is just equivalent to N. But we can show the point that I am raising with the truth predicate. So we can use the truth predicate for ZFCN to prove that to be implicitly defined over the class of all omega structures is not equivalent to explicit definability over the same class of structures. And this is very important because we are now killing one of the most important tenets of the standard theory of definitions, that definitions are dispensable. Definitions are only dispensable if explicitly defined by a finite formula, that you can replace the symbol by that finite formula. If you don't have it is equivalent to say that we have an explicit definition and to say that the definition is dispensable, that we can dispense with the predicate. It is the same thing. It is equivalent. But now we will show that we do not have dispensability in this case. So one of the tenets of the usual, the standard theory of definitions must be dropped. But we will nevertheless reinforce another tenet, which is the conservativity tenet. So let us see this. In order to recover a kind of explicit definitions, which I have called accountable explicit definition. The goal of all of this is to recover a form of Beth's theorem, which I have called Beth's countable definability theorem. And we do have this theorem, right? So that's the goal. But it's not a definition by a single formula, but a countable set of formulas, explicitly defining the predicate in some more or less the same sense that one formula defines the predicate. In fact, the truth predicate. Start with ZFCN, fix some Gödel numbering, whatever. You know. Add a unary predicate symbol V. V is for truth, for veron in Latin. And the axiom for all x, V of x implies that x is a number, right? So it is the usual setting of the discussion about the truth predicate. We arithmetize the language through Gödel numbering. It is a Gödel naming of formulas by numbers. And then we consider a predicate which is satisfied by the number of a formula if and only if, or of a sentence, if and only if that sentence holds, which I am saying formally, but formally is this. This is the truth schema. So we add to ZFCN this symbol V, this axiom, and Tarski's truth schema for the sentences of ZFCN. In our framework, the truth schema can be formulated in these terms. Phi, an arbitrary sentence of ZFCN, if and only if this says that V of the number of phi holds, right? The point is that this is just a fancy way of saying this that I will write here, because I'm dealing only with predicates, so I am not allowing proper names in my language, because this simplifies some things. So, but the way you say this is to say that, well, for everything that it is this, for every x that is corresponds to the number phi, v of x. This is equivalent to this, if you think of this as the name of the number of the sentence. So this simplifies things a little bit, right? Because we cannot write this also explicitly. We must distinguish between the Gödel numbering and the numeral that corresponds to that number, and so it is best to avoid this kind of stuff anyway. Oh, this is just Tarski's truth schema, right? And also add for all sentences phi. This is Tarski truth schema for all sentences phi, and also add this for every k which is not a Gödel number of a sentence. So if this is saying that if x is the sentence k, then x is not truth, because if x is the number k, then x is not truth, because x is not a sentence in this case. So I am just eliminating from V the numbers that are not corresponding to sentences. No, not corresponding to sentences. So for every sentence, everyone, provable or not, you have the Tarski truth schema. Phi, if and only if, V of phi. And for those numbers which are not Gödel numbers of sentences, you don't have V of that number. The resulting theory, let us call it T, implicitly defines the truth predicate in terms of the other predicates, and with respect to the class of all omega structures. This is this is the case because we don't have non-standard numbers. So that's the problem of undefinability. All elements in V must be standard, right? In the omega logic, in the omega structure setting. So this schema guarantees in every model that V is just picking the true sentences of the model. However, from Tarski's undefinability of truth theorem, there is no formula psi without V in the language of ZFCN such that T and psi define V in terms of the other predicates. So if we had one, then we would have a truth definition, something satisfying all. If you put psi here without V, you would have a truth definition here, and that's impossible. We have an argument here. It's not immediate, it's not direct, but it can be proved. Yeah.
You are now showing something that you claimed before, which is that the notion of truth presupposes an instance of the standard natural numbers, right?
Yeah.
This is a very philosophical, interesting proposal, because you are claiming that there is a essential relationship between truth and natural numbers, which is not obvious. So my question is, are you claiming that the very notion of truth presupposes an instance of the natural number, or to talk about truth presupposes an instance of natural number? And maybe these are different things.
Yeah. The point is that the notion of truth is related to the notion of formula, to sentences in your language. And you have, in a theory like ZFCN, we have, or ZFC or whatever, you have the language of ZFCN, which has these sentences, right? And you have the internalization of the language within the theory. This is a meta-theoretical object. This is that kind of concrete object that Hilbert is saying, in order to do logic, we must presuppose. Where is Hilbert's citation? It is the same thing that will answer your question. Hilbert's citation is here. No more than any other science can mathematics be founded by logic alone. Rather, as a condition for the use of logic, right? Something must already be given to us. I completely disagree with this faculty of representation, these Kantian terms. I would rewrite this as some basic agreement must be shared by us, fixing these extra-logical concrete objects. So we have this extra-logical concrete objects, right? It is part of, they are constituted in the meta framework, in the meta mathematics. And you have the internalization of them here through Gödelization, for example. This is the internal counterpart. The problem with Gödel's theorem and first order semantics and Tarski's theorem, which is the same thing. Tarski never, in his little book, he never attributes the theorem to himself. He says that it is Gödel's. The problem is that there may be a mismatch between this and this. That is, when you define the predicate of being a sentence here, the internal predicate of being a sentence here, you will have this, but you may also have other which we say non-standard sentences here. So the problem of the truth definition, right? We can make a truth definition here because we can eliminate the non-standard elements here so that we remain with this only. And then we have the truth definition. That is, truth requires the natural numbers not conceptually, but to internalize appropriately the language. The problem is that the internal discourse about truth presupposes a faithful internal discourse about the language. And this is what we get with the omega-based approach, because we have the matching between these concrete meta-theoretical parameters that parameterize our language and the internal ones. We have here a strange kind of matching, a marriage between a symbol and a theoretical object. They do not live at the same level. This is syntax, this is interpretation. So this is what Gödel has showed us. Well, we have this mismatch. The for all quantifier may admit the for all quantifier does not capture the schema. This may not be equal to this. So well, and so it is not only that we have implicit definitions in the omega logic setting that are not implicit definitions in the first order setting. We have we have implicit definitions in the omega logic setting that do not allow explicit an explicit expression. So we have an implicit definition of the truth predicate, and this truth predicate does not allow an explicit definition, even in the omega logic setting, because an explicit definition here leads to, we can show the same Tarskian argument shows that it leads to a contradiction. So I have basically written this here. There is no formula in the language of the FCN such that T and psi explicitly define V in terms of the order predicates and over the class of all omega structures, unless T, and hence also ZFC, does not have omega models. This is the contradiction contradiction that we get. So I can go to the details if that is required, but that's not our point. So now we have two approaches to our basic problem of answering what can count as definitional extension of ZFC, as a definitional extension of our basic theory. For being a conservative extension of ZFCN, implicitly defining the new predicates over the class of all structures, that is in the first order, general first order setting, is different from being a conservative extension of ZFCN, implicitly defining the new predicates over the class of all omega structures. So we have the first order based approach and the omega logic based approach for definitions, and they are different. We shall investigate both alternatives, but the later is preferred to the former, right? Because all of these examples, so definability can be treated in the same way, and also the notion of standard natural number. Well, so I think that I have already mentioned this, but yeah. The first reason for our preference is that the possibility of an unequivocal selection of an instance of the standard domain of natural numbers is a basic agreement of mathematics, right? Clearly displayed whenever we agree on what is a sequence of variables, what is a sequence of predicate symbols, right? If we agree on that, we are agreeing on the process of iteration, how this continues. Now, I can ask you, what are the individual variables of a first order language? And you will say, well, x prime, x2 primes, x3 primes. And this is considered to be an answer. So why? Because we have an agreement that, okay, we agree that this is, this gives us the sequence of variables. Because we agree on an arbitrary point how to continue. How to continue from an arbitrary point of the sequence. Of course, this presupposition is clearly displayed whenever formulas, which all these objects are obtained by iteration, considered within the meta-theoretical range, are defined, right? We consider that that kind of thing defines the variables of our language. This is a definition, right? If I ask you what are the variables of your language, you give me this definition. So this is Hilbert. We have already seen this. Second reason. Well, besides the definition of standard domain of natural numbers, other important mathematical definitions, like the definition of the truth predicate, cannot be accomplished if the class of all general first order structures is fixed as our interpretative basis. Also, Hilbert's idea that a mathematical theory, not necessarily finitely axiomatizable, implicitly defines the class. John has talked about this with more carefully. But I take Hilbert's view to be the structural definition. So a mathematical theory, Hilbert says, and there is some famous quote in which Hilbert says that a mathematical definition implicitly defines its primitive terms. So, and there are two interpretations on what Hilbert is saying, and I take it to be that any mathematical theory can be seen as a definition, right? A definition of what? A definition of its class of models. It is the only thing that is unambiguously fixed by the theory. But this is not a standard definition if the theory is not finitely axiomatizable, because, well, if you think about it, yeah, it's not a finite definition. It is not a finite definition of the class of models. It is more something like this, not like this. Indeed, we may think that a theory is defining, a theory as a whole is defining a condition, let us say, a condition that is met by its models and is not met by the non-models, right? A theory is defining a condition. We could say a proposition. Which proposition is this? If these are the axioms of the theory, which condition is met by its models and it's not met by the non-models? The condition is just this. The problem is, if the theory is not finitely axiomatizable, that is not a sentence. However, I am only considering countable theories, right? As usual in mathematics. Okay. But if we are on the omega structure based approach, we have a definition of that condition, and it is the short proof is that, well, this is an L omega 1 omega sentence, and then we can interpret it in omega logic. That's it. There is a longer proof. That is, do this explicitly. Now we can do this. Third reason. This is about mathematical, the difference between mathematical validity or mathematical truth and logical truth. So, logically valid is not the same thing as mathematically valid. This is the point of for example, the first Gödel's incompleteness theorem, that this theorem is usually formulated as saying that there are truths that are not provable. There are mathematical truths that are not provable, because logical truths are always provable by the completeness theorem. So there are two senses of truth here, so that we must distinguish: mathematical truth and logical truth. And what comes closer to mathematical truth? Well, the omega structure based approach. For example, Gödel's sentence is true in this class of omega structures. Of course, it will not be provable if we maintain the syntax, if we do not add the omega rule, as John will correct me in a minute, so let me say in advance. So if omega rule is not added, which we can go full omega logic, say that a mathematical theory has two layers, as I have said, the symbolic layer and the semantic layer. I am taking the semantic layer to be omega logic, and I am keeping the symbolic layer to be first order logic. We could choose to do both moves, the symbolic layer also omega logic. I see only a problem in doing this. The use of omega rule, even a single use of the omega rule in a proof, right? If we allow the omega rule to be used in our proofs, even with the restriction that only once, gives rise to a non-recursive notion of proof. If it is non-recursive, it means that it cannot be mechanically verified. And this is a feature that usually is considered to be important. Well, to formulate a mathematical proof, of course, is not something mechanical. This is we understand as something hard that, well, is not a mechanical task. But to verify a given mathematical proof is usually understood as a mechanical activity. If we adopt omega rule, this is lost. So I call this the recursivity requirement on proofs, right? And so that's the reason, but I am not discussing proof theory here. This book is about definitions and about the interpretative dimension of mathematics. So I have deliberately chosen to keep the syntax intact. But it is an important and interesting discussion. So, but then if mathematical truth is understood as validity with respect to all first order structures, then, well, mathematical truth is logical truth, and truth is logical truth is provable. All logical truths are provable by Gödel's completeness theorem. But that's not the usual reading of the incompleteness theorem. Mathematical truth is not usually taken to be equivalent to recursive probability. So, on the other hand, validity with respect to omega structures agree with that reading. So, making both, for example, Gödel's sentence and the standard consistency statement true, right? Under the usual assumptions, but unprovable. Well, here we have a conservativity issue that I will will probably not enter this discussion, but conservativity is not enough for our definitional extensions. We must impose on them a stronger condition that I have called strictly conservativity. And well, that's a technical issue that I maybe will skip. And then tomorrow, I think that I have already discussed the issue of classical rationalism, the idea that mathematics is about knowledge, is about truth and justification, and definition has everything to do with truth. Right? We have defined the truth predicate, but not only. We can indeed from truth we have a definition of definition, and from the conception of definition we can also recover truth, because a sentence is true if it defines a true proposition. That's the point. So a true sentence is a sentence which explicitly defines the proposition that it explicitly defines is the true proposition, that is the predicate that is always true, so, or true in all models. So truth and definition are exchangeable, and mathematics is about the truth ideal, even if it will never be attained. So it is like the Kantian famous quotation, right? Out of the crooked timber of mankind, no straight thing was ever made. So maybe we are on that crooked timber chain and cannot reach the absolute knowledge ideal, of course, but nevertheless mathematics is aimed towards the ideal, even if it is not reached. But we have also this normative expressivist view of mathematical theories as rules for the practice, and as rules for the practice, our claims of mathematical truths, which are always partial truth, are nothing but claim to commitments to the rules. So we are definitely not historicists, but of course everything begins with history, and so we have to take this into account. And well, we have a view of mathematics as theoretical, not an artist construction with drawings and stuff like that, but linguistic science. And well, that is our, I think that concludes our main conceptual framework. In the next section, we will start with first order definability theory, and we'll okay. So thank you.
Rodrigo, thank you so much for your talk. Amazing. I have a question about the minimal assumptions for your logic. Am I right that the iteration itself actually to make your omega system working also needs a zero, the starting point of iteration, right? It also needs the true identity of symbols rule, and it also needs actual infinity. I think so. Is it correct? Yeah.
Well, I have dealt with the infinite issue that was raised by Giorgio yesterday by appealing to the iteration notion, right? When I say that we have an agreement on the notion of standard natural number, for example, I am not saying that we have this infinite agreement here. What I'm saying is that we have an agreement on how to iterate an operation. So we have this operation of taking the successor. And our agreement is just like that. At any point of this sequence, we know how to continue. So this is the potential infinite. The potential infinite is not an infinite, and it is not a set also. The potential infinite is the process of iteration itself. And so I think that this point does not commit ourselves with actual infinity, but in a sense, of course, I am committed to actual infinity in the sense that there is a mathematical practice of talking about the actual infinity. So I am committed to the reality of mathematical practices. And one of those practices is the interpretative practice, according to which mathematicians discuss all kinds of structures, including set theoretical structures with many sets in there. So so in this sense, I am saying that I am committed to actual infinity is saying that I am committed with the real mathematical practice. Yeah, I take the reality of these practices, but not that we have some infinite sets that are not in contact with our practices. So I do not need any infinite set which is not in contact with the usual mathematical practice. So in this sense, I don't know if which one of the questions are you asking, but there are, I think, in my view, two separate questions here. And about the zero, no, we don't, but the process of iteration does not require a zero starting point, but the practice requires a starting point. We must lay down language, and so we must we start at some point. So I think that's it. So the difference between the of course, plain first order logic also have the same kind of commitments. So the omega logic based approach adds just one more commitment, the commitment to the standard natural numbers. So, but in the standard first order logic approach, you are already committed to first order structures. So there are, of course, many this semantic agreements that I am talking about are not only related to omega logic. They are also on the basis of first order logic also.
Questions?
I'd like to do two things. One, I don't think I was clear at the end what I'm going to do tomorrow. And tomorrow I'm going to go away from the geometry for a bit and introduce a new omega rule that was ascribed to, and prove that the consequence of this new omega rule is a categoricity of piano arithmetic, or even of Robinson's Q, and also you can interpret L omega 1 omega into this logic that is first order logic plus a new rule, and then and so get away from the objection to L omega 1 omega that there are infinite formulas, because using only finite formulas but an infinite rule, you get the same information. And then getting back to your question, I'm confused when you talked about the infinitely axiomatized. Were you saying that somehow needed the standard rule? Because this is what we do all the time, right? We have infinitely axiomatizable theories, most of them, and I don't know what are you saying that is different with respect to the omega?
To the omega rule?
Yeah, well, to the omega model.
Yeah, the point is we have infinitely, not finitely axiomatizable theories, right? Take one example, the replacement axiom that I have mentioned. Okay, and so, and also we have Hilbert's thesis that this is a definition.
This is a definition, you say?
This is a definition, yeah. Infinitely many axioms define something. This definition, of course, is not an explicit definition, because, well, an explicit definition presupposes an explicit defining sentence. What is the defining sentence here? Well, the defining sentence, my answer is this infinite conjunction. This is the defining sentence. But this is, of course, not a sentence in first order setting. So what we can do, right? We can read this in the L omega 1 omega setting and then translate, as you mentioned, or I will use, as you know, Chang's result on the omega projectivity of L omega 1 omega to introduce this as a pseudo-elementary class in omega logic. We have here an elementary class in L omega 1 omega that will be pseudo-elementary in omega logic. So in omega logic, this is indeed a definition. This is we are defining the class of models. The class of models is defined by that defining sentence. But that defining sentence is not a sentence. That's the problem in our framework. So we must turn it to a sentence that will define this. But the definition will be pseudo-elementary, right? An implicit definition that will be pseudo-elementary. And we can do this. We can do this. This is a theorem that is in the book. But the idea is just very simple. It is just this.
I think that in Chang's theory, once we made the translation to Chang, it's not a sentence. It's back into a theory.
Yeah, you are back to a theory, but I can have a sentence. Yeah, I can have a sentence with Chang's. We have a lot of Chang's technique is to add additional predicates. So this is the projectivity part, but in the end you can have one sentence with that background, the background theory. This sentence is equivalent to this, but with the background axiom. So it will be a definition inside a theory, but it will be a definition. We can also see this as this is defining a condition, a predicate, but a predicate that is zero-ary, a zero-ary predicate or a proposition. This infinite stuff is defining a proposition. What is the explicit definition of this proposition? It is just this is equivalent to this. In L omega 1 omega, we have the explicit definition of this proposition. I will translate this explicit definition to omega logic. I can do that with Chang. We will have an explicit definition, but it will be within a bigger theory. But we can make sense of the idea that not finitely axiomatizable, non-finitely axiomatizable theories are definitions of zero-ary predicates, which is P is the characteristic function of the class of models. It is 1 for the models in the class and 0 for the models which are not in the class of the structures which are not in the class. And this will be in plain omega logic. We don't need even the apparatus of ZFCN to define this. Tinha rapaz que queria. Você, se quiser perguntar em português, pode também.